All right, if you remember in Algebra 1, we learned how to solve equations. We did things more complicated than this typically, but this was the idea. We'd solve equations, subtracting 3 from both sides and getting one value. And then after that, we jumped to, okay, what if it's not an equation? What if it's an inequality? So something like this. So now the answer to this is not just one value, but it's multiple values. So I still solve it the same way, but now instead of one x value, I get a range of values, anything bigger than 4. So that means anything bigger than 4, I can plug into x, and that'll make this left side bigger than 7. That's what it's saying. As opposed to, I have to plug in exactly 4 here to get exactly 7 here. So that's the difference between inequalities. And if you remember, the only issue and difference with inequalities in solving was when you had an inequality like this, and you divided through by a negative number. If you divided or you multiplied by a negative number, then you had to flip this sign around. So instead of less than, now it becomes greater than or equal to -2. So that's just kind of a review of the issue with inequalities is multiplying and divided by a negative number creates a problem. So what we're going to do in 3.7 is we're going to look at inequalities with polynomials and rational functions, the two things that we've looked at in this chapter. So let's start with a rational function and make this an inequality. And typically, if this was an equation, you would take this and you would clear the fractions. And so you'd multiply through by the denominator. Okay, that's what we did to find the x-intercepts on these. And I would say x plus 3 is greater than or equal to 0. Here's the problem. My question is this. This value that we multiplied by right here, is this positive or negative? Because it matters, right? Because if this is a positive value, then I keep the sign the same. But if this was a negative value that I multiplied through by, I would have to switch this. So the question is, which do I do? And the answer is, I don't know, because I don't know what x is. If x is, say, -4, then this quantity is going to be negative, and we have to flip the sign. But what if x is 10? Then all of a sudden, this quantity is positive, and we don't flip the sign. So the problem with rational equations and polynomials and inequalities is that you cannot multiply through by an x term. Okay, so I'm going to write that rule here in orange. You cannot multiply or divide by an x term, or any combination of x terms, x minus 2 or anything with an x in it. You cannot multiply or divide by that because we don't know if you flip the sign or not. So we need a different strategy for solving these problems, and this strategy that we have done in the past is not going to work. So in order to create a new strategy, let's actually look at what we're doing. I'm going to take this equation, x plus 3 over x minus 2 is greater than or equal to 0, and I'm going to treat this right here like a function, and I'm going to graph it. Okay, now at this point, you can use the graphing calculator to aid you. You can find your x. Graphing this should be fairly quick by now. You've got an x-intercept of -3. That's where the top equals 0. You've got a vertical asymptote at 2. That's where the bottom equals 0. Your y-intercept is going to be -1.5. That's where you plug in 0 for x. And your horizontal asymptote, if you take the limit as x goes to infinity, we divide everything by x, and we get 1 plus 3 over x over 1 minus 2 over x. These go to 0, and I get 1. So I've got a horizontal asymptote right here. So this equation, or this graph, if we look at it as a graph, has a swoosh there. I cannot swoosh down below on the right because I'll create another x-intercept. So I'm going to swoosh up top. Now, what is this asking? This inequality is saying, I want to know where this function that I just graphed is bigger than 0. So here's 0, because we're looking at, yeah, okay. And where is this bigger than 0? So this is going to be bigger, and down here is going to be smaller because these are negative values, these are positive values. So where's that function bigger than 0? Well, it's bigger than 0 right here in this little section, and it's also above the pink line here in this section, okay? And it's below in this section right here. So I can write some intervals. I'm asking you, where does this happen? So that means I'm looking for x values. So this x value right here is -3. So I'm going to say from -infinity to -3, I am above the line. And from, it looks like 2 on, I'm also above the line. Now, do I do square brackets or round brackets? Well, I go back up here and I'm like, okay, that's greater than or equal to. That means being 0 is fine. So where is this graph exactly 0? Well, that's here. That's exactly 0. So that means this bracket's going to be squared. But at 2, the function's actually undefined. So this one stays round. All right, so I'm going back to the graph to figure out how to square the brackets. And this turns out this is my answer. So what am I looking for? Well, what we call these points right here and right here, we call those critical points. Critical points are where the function is 0 or undefined. So they're the vertical asymptotes and they're the x-intercepts of the graph. And those are the places that the graph potentially changes from positive to negative. So this is a great section because not only do we look at inequalities, but we also get some extra practice graphing. Okay, so if I were you, I would go through some of the steps and show some work as to what you're calculating, and then check your graph with a calculator and then pull the parts that are above or below the graph off. So let's do a couple more examples. Okay, but before we do that, I want to set you up a list. So solving inequalities, and this is for rational functions, and it'll be the same list for polynomials. Okay, the first thing that you have to do is get everything on one side. And we're going to do that by addition and subtraction only, because remember, you can't multiply things across. So you're just adding and subtracting terms over to one side. Why do we do that? Well, because comparing to 0 is the easiest place to compare to. That's our 0 is this line right here, which is the x-axis. And when this is 0, then your critical points are x-intercepts and vertical asymptotes, which are easy to find. If you compare to any other number besides 0, you actually have to calculate where the function's crossing that line, which is a little extra work. So it can be done, but this is the fastest, easiest way, is to get this function set equal to 0. So this example already we didn't have to do that, but examples in the future will not be. So we're going to get everything on one side. So we're going to set it equal to 0. And then we are going to combine all fractions and or simplify. Then we're going to graph it. And we're going to write the intervals where the graph is above or below the line, depending on the inequality. Okay, so this would be a note card right here. On the front, I would put, how do I solve inequalities? Maybe write an example of a function on the front. And then on the back, I would create some sort of list like this to help myself. Let's do an example. I'm going to do x over 2 is greater than or equal to 5 over x plus 1 plus 4. All right, let's use our list. So first thing I want to do is get everything on one side. So I'm going to get everything onto the left, and I do that with addition subtraction, which means I'm going to subtract this whole thing over. You can get it all on the, sorry, I'm getting it on the right-hand side. You can get it all on the left too, it does not matter. The next thing I need to do is combine all fractions and simplify. So that means that I need a common denominator. So the 4 is not in fraction land currently, so I'm going to put it over 1 to get it in fraction land, and then I need a common denominator. So I'm going to multiply this one by x plus 1 on the top and the bottom. Now it's worth noting at this point that what I'm doing in getting a common denominator is I'm multiplying one fraction, top and bottom, by something, which is this value right here is 1, because x over 1 over x plus 1 over x plus 1 is 1. So I'm not changing the value at all, and I'm not violating my issue because I'm not actually clearing the fraction. When I clear a fraction, I multiply the left-hand side and the right-hand side by something that's the same. And I'm not doing that here. I'm multiplying by an x term, but it's only on one side, top and bottom. So that doesn't affect flipping the sign. All right, and then I'm going to take this 4, and the 4 needs a 2 and an x plus 1. And then this first term just needs a 2 on the top and the bottom. All right, so let's multiply that out. And as I go, I'm going to multiply as I go and combine the fractions. So I've got a 10. And then this is going to be 2x plus 2. And then I'm going to distribute in this positive 4. So I'm going to get plus 8x plus 8. And then I'm going to take this negative x. Remember to bring the minus sign with you. The minus sign distributes in. So I've got a minus x squared and a minus x. Those are all my numerators, all over my denominator. In this class, don't ever multiply out your denominator. We want it to be factored so that things cancel. And if we need to multiply it out later, we can, but 95% of the time, you don't want to multiply that out. I'm going to simplify the top of this. So let's see, I've got a negative x squared. I've got an 8x and a minus x is 7x. And then a 10 and an 8 is an 18. Over 2 times x plus 1. All right, now I'm ready to go, and I want to graph this thing. So I'm going to find my x-intercepts first. My x-intercepts are found by setting my numerator equal to 0. Personal preference, I don't like factoring things that have a minus sign in front of the x squared. So I'm going to take this and I'm going to divide everything by a negative 1. So that's going to change all my signs. You do not have to do that, but I like doing that so it helps me look at it clear. So I'm going to go, let's see, x minus 9, x plus 2. That's going to multiply to give me negative 18 and add to give me negative 7. So my x-intercepts are at 9, 2, 3, 4, 5, 6, 7, 8, 9, and at negative 2. These are x-intercepts. My vertical asymptotes are at x equals negative 1. That's where my denominator equals 0. My horizontal asymptotes, remember that is helpful to look at with everything multiplied out. So I'm going to take the limit as x goes to infinity of negative x squared, 7x, 18, over 2x plus 2. I'm dividing everything by x, and if you have noticed the patterns by this point, the power up here is higher than the power down here. So you're going to be left with an x. This turns out to be a negative x. This will be a 7. This will be 18 over x, 2, and 2 over x. So this is going to make it go to infinity and give me no horizontal asymptote, which means that this potentially has a slant. So let's check that out. So we divide negative x squared plus 7x plus 18, and we're going to divide that by 2x plus 2. So what do I multiply 2x by to get negative x squared? The answer is negative 1/2, because I want that 2 to go away. So I multiply that out, I get negative x squared minus x, and I'm going to change both of those signs, plus plus. So these cancel, and I get an 8x plus 18. And then the last thing is, what do I multiply 2x by to get 8x? And the answer is 4. So this is going to be my slant asymptote. I've got a y-intercept of 4 and a slant asymptote of 1/2. So we go kind of like this. All right, and then we need y-intercept. If I plug in 0 for x, I get a negative 8 or positive 18 on the top, and then I get a 2 on the bottom. So my y-intercept is a little off my graph up here somewhere. Okay, so my swoosh is up here and it crosses over there, and then I've got a swoosh down here like this. Okay, the question is asking, now look at how it's facing. We're going to look at it right here. Where is the graph? The graph is on the right. Where is the graph smaller than? Because the small end is pointing towards the graph. So I want to know, where is the graph smaller than 0? So this means, where is it below the x-axis? And the answer is in this little region right here and in this little region right here. And I name those regions with x values. So where are they? They're going to border with the critical points. So negative 2 to negative 1, that section, and then 9 on out. So my answer is going to be negative 2 to negative 1, and then 9 to infinity. Now let's check out the signs, or I mean the brackets. This is an or equals to, so that means I have potential for square brackets, and square brackets come at the x-intercepts. They're the places where the graph is actually at 0. So negative 2 and positive 9 are going to get square brackets. Infinity always gets round, and negative 1, because it's a vertical asymptote, gets a round. So this is my solution. Now, I don't care if you use a calculator to help you graph this, but if on a test I ask you to show your work for your asymptotes and your x-intercepts, you need to be able to show me this work here and use your graphing calculator to check yourself. All right, let's try a polynomial. Polynomials work the same. In some ways, they're a little bit easier because you don't have to do all the adding fractions. So let's do x squared, 7 minus 6x, equal to 1. So same rules apply. I want this set equal to 0, so I'm going to take this 1 over to the left. And I'm also going to distribute this in because we're going to have to refactor it anyways. So I'm going to get 7x squared minus 6x cubed minus 1 is less than or equal to 0. Minus 6x cubed plus 7x squared minus 1. I'm just putting it in order. And now I need to find critical points. Critical points are x-intercepts. These things aren't undefined anywhere because there's no fractions. So all I'm really interested in is, where are the x-intercepts? Those are potential places where this function would change sign. So in order to get the x-intercepts, I have to set it equal to 0, and that means I have to factor. So it's a cubic. I'm going to need to use synthetic division. Isn't this cool? It's all coming together. You're using all the tools. So my cube term is -6. My squared is 7. My x term is missing, so I need a 0 there, and my constant term is 1. All right, options. Unfortunately, we might have fraction options. It's divisors of 1 over divisors of -6. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. So this is setting us up for potential fractions. It's all right, you can do it. I'm going to try 1 first and just hope for the best. 1, 1, 1. Oh, look at that. We got lucky. All right. So 1 works. So that means x equals 1 is a solution, which means x minus 1 is the factor. And then my remaining factor, this is my remainder, my constant term is 1, my x term is 1, and my x squared term is -6. Okay, so one of my x-intercepts is going to be 1. And the question is, what about the other? Can I factor, let me move this down a little bit. Can I factor this? I'm going to play with it for a minute. 3x, x, and if I'm going to go, oops, not, this is going to be a 2. So if I do a +1 and a -1, oh, they both have to be positive in order to work. Let's see if that works. This is a -3 and a +2. Or they could both be minus. Let's try that. This is going to be a +3 and a -2. That works. Okay. If you multiply that out, you can confirm that work. I'm just doing that again in my head to make sure. Yep, I think that's right. Okay, so that means that I'm going to get a -1/3 as this solution, add the 1 over, divide by -3, and then I'm going to add this 1 over and divide by 2 and get 1/2. Okay, and so my graph, these are all single roots. I'm going to increase my scale a little bit. I'm going to make this 1. 1, 2, 3, 4. Make this -1. So here's -1/3. And here's a half. They're all single roots. My y-intercept looks like if I plug in 0, 0, it's going to be a -1. So I'm coming down here. Whoops. Almost did a little black magic right there. Don't worry, I caught myself. Okay, it looks like we're looking like this. Now, here's what checking yourself looks like. I'm going to take this this graph right here. I'm going to go over to my class calc and try it. -6x cubed plus 7x squared. -6x cubed plus 7x squared and -1. All right, so this is what it's looking like. I've got, if you want to tap on these, you can see I've got an x-intercept of 1 and a half and a -1/3, and it's coming down from the left. Well, looks pretty similar. Okay, so that confirms my work there. Now, what the question is asking is, where is this function less than, the small end's pointing towards the function, 0. So where is this below the x-axis? So it's this little section here is below the x-axis, and this little section here. And that's going to occur at -1/3 to 1. or excuse me, 1/2. I needed to pay attention to my scale, 1/2. And from 1 to infinity. Infinity always gets round brackets. Now let's go up here. This is or equal to, so it's potentially every place where I have an x-intercept is a square bracket. Well, all of these are x-intercepts. So these are all going to get square brackets. And that is going to be my solution. Okay, and the polynomials don't stray very far from this. They're all going to look really similar. Some of them you can factor by grouping or greatest common factor, but they're all just going to factor up and give you your x-intercepts. So practice these. It'll give you some extra practice graphing. Check yourself with your calculator, and I'll see you next time.